Welcome, everybody, for our next edition of NITheCS Colloquium. Our today's speaker is Dr. Amartya Goswami, who is going to speak about from rings to lattices. I will briefly remind you of his biography. Dr. Goswami is affiliated with both the Department of Mathematics and Applied Mathematics at the University of Johannesburg and the National Institute for Theoretical and Computational Sciences. His current research interests encompass associative rings and algebras, general topology and order, lattices, and ordered algebraic structures, pure mathematics. He has authored 20 peer-reviewed articles and has delivered 37 talks at national and international conferences, seminars, and workshops. Since 2016, he has co-organized a special session on categories algebra, topology, and logic, CATL, at the South African Mathematical Society SAMS annual congress each year. So welcome again to all the online participants and to the in-person participants, and we look forward to your talk, Dr. Goswami.
Thank you very much, Zurab. Can you hear me? Or should I speak louder? Is it fine? Okay. Thank you very much for the kind invitation by NITheCS. I really appreciate that. And the idea is here to talk with you some of the recent works which I'm working with other people as well. But please forgive me, this colloquium is supposed to be at the level that everybody can understand it from the very beginning up to the end. The bad news is that if you are not from pure mathematics, then could be difficult. So I apologize for that. But fortunately or unfortunately, I will be here for this whole week at Stellenbosch. So in case if anything I said attract your attention or you like to know more about or talk about, then I will be very glad or honored to talk with you. Thank you. So that is the whole idea here. So the talk will be based on mainly two mathematical structures. One is rings and rings type of structures, and then lattice and lattice type of structures. So let's see why actually we are here. I wanted to share some observation and ideas on various types of ideals of rings and that their corresponding extensions with the different type of special type of elements in some special type of lattices. Probably you have noticed that I put inverted commas on the rings. I wanted to mean that ring or ring-like structures, and of course it's a very vague term when I say ring-like structure. I wanted to mean more specifically rings, hyperrings, and rings not necessarily means associative rings. It could be non-associative rings and algebras. It could be monoids. It could be semigroups and so forth. Okay, so this is the first goal of this talk from the mathematics point of view. The other is since this is a part of the NITheCS program, and I'm associated with the mathematical structure project for a couple of years. So one of the goals of the NITheCS is to create new collaborations between different areas whenever it naturally possible. So I will try to convey a message here that even with some pure mathematical areas, one can still think how to connect between different pure mathematics areas, and also some of the mathematical structures naturally appears in other sciences, like more specifically in mathematical physics or physics in general. So that could be some possibilities or opportunities which Professor Francesco Petrucciano is telling us again and again. Maybe from here we can think of new kind of collaborations between interdisciplinary, or rather what he said, undisciplinary kind of things, I mean, at the second stage of it. Okay. So Of course, this work is not done by myself, and I have some partners in this crime. Why it is cutting? Okay, the first one is Professor Theba Dube from UNISA. The second one is Bijan Davaj from Iran. Third one is, many of you know, she was here now in AIMS, Professor Karin Howell. Fourth one, I think I shouldn't mention who is he. All of you know that. Sitting here, Professor Jurab Zainalize, and then Professor Carmelo Finocchiaro from Italy. And there is another collaborator whose picture I couldn't find over the internet, and I requested him for his picture. His name is Dr. Dario Spirito. I still didn't get his picture, but anyway, you can recognize his works from the internet. And then a few students, Ineke from Stellenbosch, Michaela was my master student from University of Johannesburg, then Daniel from here, and then Kerry is also from here. The last two is very special with respect to the NITheCS that last year they came through internship program to University of Johannesburg, and both of them probably they participated in the Olympiads in the international level, and so they are already very well known in Stellenbosch. And my idea was just to give them some exercises in ring theory for 5 days, just to let them know what is a ring. And I thought that will keep them busy for the whole week, and then they finished all the exercises in 46 seconds or something like that. So, and then we started proving theorems, absolutely new theorems. So they are really very, very excellent students. Thanks to all of you who are teaching these mathematics modules. So first of all, when we talk about ideals of rings or ring-like structures, first question is, do you have enough different types of rings, ideals? And believe me, these are not the typos, what you see, these alphabets. Once I was heard few ideals called Z ideal, D ideals, from Professor Dube. Then I asked, is it really true that for every alphabet there exists one notion of ideal, either in rings or any other algebraic structure? And to my utter surprise, yes, at least one notion of an ideal called A ideal, B ideal, C ideal, D ideal, like this way. And all these ideals actually been defined mostly for rings, but some of them are for other algebras. And then we have many of these known types of ideals, mainly for rings, and some of them appears in function analysis, some of them appears in non-associative algebra. Even some of them are called ideals, but they are not ideals in the usual sense. For example, inner ideals in Lie algebras. So we have, and of course, this list is not finite in some sense that I do not put everything, just a sample. So we have plenty of different types of ideals came out for different reasons to study these algebraic structures or involved in that algebraic structures. So the question is, if we pick up one particular type of ideals, of course, among all these ideals, one may ask, which one is the most important ideals? I mean, that's very controversial question. But in general, from the applications point of view within the mathematics, prime ideals is one of the most useful or applied classes of ideals because of this algebraic geometry purpose, etc., etc. But nevertheless, other ideals plays their role in their understanding of the corresponding structures. So how to work with a type of ideals, in the sense that if you pick up one classes of ideals which has been invented, or we already you invented something, how to work on this. So let's take a ideal type of ideal which is not even for ring, for semi-ring. So what is a semi-ring? Semi-ring is you just forget about there is no subtractions in your ring. So you can have these two monoid structures, and then they talk with each other, something called distributive property. And you can have commutativity, you can have identity, depends on how you wanted to work with that. And since there is no subtraction in semi-ring, there is a way to understand how can we convey that message that. And then Melvin Hendrickson actually in 1960s came up with this notion of K-ideal. So since you cannot have x minus y type of things, so we pretend that if x is there, x plus y is there, then y is there. So some kind of subtraction, you compromise in some sense. So this is a very well studied class of ideas for semi-rings. And many of you who works on general topology or categorical topology or even point field topology or lattices, one of the interesting thing for you is the closure operator, which we generally introduce and study various properties. And this K ideals also has a very natural definition of a closure operator. And then you can actually endow this closure operator on all ideals. And then what is interesting about this closure of this I, it will be the smallest subtractive ideal containing the ideal I. But then you may ask that why should I bother about this introducing the closure operator, and why, or rather, what is it good for? It is good for studying many different types of special type of subtractive ideals. For example, if you have a prime subtractive ideal, if you have semi-prime subtractive ideal, then you can actually show using this closure operator that sometimes you do not need to check prime and subtractive separately. On prime subtractive will be sufficient. So this kind of applications you can do with the closure operations. So So here we actually can see how different types of ideals are connected with each other in terms of K ideals or the subtractive ideals. So there is already a notion of prime ideals, semi-prime ideals in rings, and similarly we can define them for semi-rings. Now we can restrict these kind of ideals for the subtractive ideals. And then we ask the same questions that how these type of ideals are related. It's very similar what we are seeing in for rings case. So this is a typical property which we actually study for that. And this equivalence between radicals and semi-prime and the intersection of prime ideals, if you remove all the K words, this is a very well-known result in non-commutative rings. The question is, can we do the same kind of things for the semi-ring and more specifically for this special type of K ideals? And it turns out, yes, we can actually prove the things. And the good thing is that because of the commutativity structure, some of the proofs become much easier. And semi-ring also plays little bit different role compared to the ring. Similarly, one can actually show that how this primeness, semi-primeness, and strongly irreducible ideals are connected with each other. When we say the strongly irreducible ideals, it's very important, at least from the topological point of view, that if you have heard of the Zariski topology, then that Zariski topology, which generally appears in algebraic geometry mainly, that topology we put on prime ideals. The question is, what is the largest class of ideals on which you can get Zariski topology? And the answer is actually strongly irreducible ideal, because their definition is built in such a way exactly how you this get the closeness property for the closure for the closed sets to get the Zariski topology. So the general connections of these nice classes of ideals is like this. You have maximal ideal, then you have prime ideal, and then you have strongly irreducible ideals. And if your ring is non-commutative, then something comes in between here, which disappeared in a commutative case, and that's called primitive ideal. So maximal, primitive, prime, and then this strongly irreducible ideal. So these are the good classes of ideals where you can nicely get topology and study all this, but you cannot go beyond this strongly irreducible ideal because it will fail this closureness property. Okay. So with this one, we captured all these results and many more actually in this paper with Themba. This is actually a second study. The first one actually done in 2019 by three people on these K ideals. And we wanted to study further properties on K ideals of these semirings, like what I said. And to best of our knowledge, we wanted to use specifically these closure operations, which to us is quite fruitful to study special type of uh, classes of ideals. Okay, now what are the setups to do the extensions of ideals to elements in lattices? So what we wanted to do, we have seen many classes of ideals in rings, semi-rings, and these things. Now the question is, we wanted to do similar kind of things for lattices. So now we do not take ideals anymore, we take special type of elements which have the same flavor as the corresponding ideal. So first let's see what kind of lattices we talk about. So we start with a complete lattice and then we have different setup. So let's start from the bottom. The bottom is that you have a complete lattice and with a multiplication operation such that the product of two elements is below their mid. And this is one of the very first Carl's works appears this notion. Of course, in that time the terminologies and the approach was not like how we write today, but essentially it captures there. And to see specifically the prime elements, which I will define shortly, which is mimicking the corresponding notion of prime ideal. To see these prime elements in this most general setup, one of the most comprehensive and in fact the most comprehensive paper written on this prime elements only very recently in 2019, which covers not only the algebraic aspects, it covers topological aspects, it covers categorical aspect and everything. And it's by Professor Giannalise and then Finocchiaro, the picture what I showed, and then Professor Facchini. Both of them are from Italy. So that paper actually gives a complete account of the study of spectrum of prime elements on this most general setup of these multiplicative lattices. And the second one is more recently in 80s, Mulvey came up with that because he wanted to do some kind of non-commutative geometry setup in quantum mechanics. I have no idea for the quantum mechanics how that applies there, but that's the way how we wanted to introduce that. So only the thing is that the star becomes or the multiplication becomes associative and it distributes over arbitrary joints. And the top one is actually older than the second one, and it's from 1960s. And that's actually Dilworth and Ward came up, and that's exactly where they use the terminology multiplicative lattices. So you put more conditions there, so your multiplications become commutative. You have multiplicative identity. So who is your multiplicative identity? Just take the top element of your lattices, and then exactly have the same distributive properties. Now, those who are working on point-free topology, you can immediately see this, the top one, if you replace your multiplication by mid, that's nothing but your frame. So of course, frame is a special example of this setup, what we are talking about there. So, I mean, we immediately have a very vast field of study, both algebraical and topologically, of these multiplicative lattices in a more general setup. But since we are interested on this ideals type of study with lattices, frames is not quite right choice of the structure because your multiplication coincide with your meet operation. So you do not have two different operations there in some sense. So multiplication also plays some role. And we will see an example that how in frames two different types of elements coincide because of the lack of the multiplication. Okay, so we have seen these quantales, which is the second most general study on the lattice type of structures, so which is most widely used in different areas of mathematics and physics as well. So the question is why quantales? Because if you actually search the literature, you will find examples of these quantales in all these areas of mathematics as well as in physics. For example, I will give you example few, but for the various kind of studies, quantals naturally appears. And since this algebraic structure appears naturally in various areas of mathematics as well as in physics, this could be the possible connecting path for new kind of collaborations or uh, discussions between different areas, which generally we don't see, because we wanted to see a natural framework where we can talk with each other, not artificially create something. Okay, let's talk, so let's create something like that. So this could be one such things based on the our NITheCS idea as well. So here are a few examples of quantals. And for example, if we see the last one, that immediately tells us that if you are working on function analysis, we have a very natural examples of a quantals of a sister algebra, and you take the closed right ideals. Of course, you can take the left ideal similarly. Since we dropped the commutativity, of course, we can talk about left and right. If we introduce the commutativity, of course, you can just talk about the ideals. And of course, frames, we already mentioned that it will be a special case of quantals or multiplicative lattice, depends on what terminology you like to use. Okay, so we said about ideals in rings or ring type of structures. The question is, can you also define an ideal in a quantal? Yes, we can define an ideal in a quantal. So we just try to copy what we have done for ring. So in ring, if we have two elements x and y, their sum should be there. So sum will be replaced by their join. And then it's something called the bounded below, that if some element is there and something is below that element should be there. But if you are working, of course, I took this definition and the setup of multiplicative lattices for simplicity. Uh, and that plays something interesting role here, because if you are working already in lattices, probably you may say, but wait a minute, this is exactly the definition of ideal in a lattice. But you said you are working in a multiplicative lattice, so you have an extra multiplication operation. So why that operation does not contribute anything to adding a new axioms here? And because the magic is happening, because this inequality actually helps to get this product operations, that in ideals we take an element from the ring, we take an element from the inside ideal, then you take the product and then it's there. And that property comes free because of this property holds there. So that's why these two definition of ideals in a normal lattice and in a multiplicative structural lattice, they coincide. So it's not actually some miracle is happening just because of this simple inequality is there. And by the way, this inequality also plays a role when we talk about topology and get the closureness property. So it's a very, very important and vital one. Uh, then we actually did some study on this type of various types of ideals on quantals itself, both algebraically and topologically, and see how much you can do ring type of things in the quantal setup. Now something I have to go down. Okay, now let's take a concrete example that if you have a certain type of ideals, how to convert it into the corresponding type of elements. So here is an example. Okay, let's take the corresponding inequality in the ideal. If we know the product of two ideal is always smaller than their intersection. Now, how to convert it the corresponding element? Just take two elements and their product should be below their mid. So just replace this intersection by their mid and then you get the corresponding version. Now, the second point on the left-hand side, that's exactly the definition of a prime ideal. So what is a prime ideal? If the product of two elements is there, then one of is there. Now we wanted to convert it the corresponding prime element version. So this was ring, and now we wanted to do the lattice. So we exactly do the same thing. We take the product of two elements, which is below, then P, then one of them is just P. The third one is called actually strongly reducible ideal. And it's a very strong condition that if the intersection of two ideals is contained in that ideal, then one of them is contained in that ideal. So we can exactly copy that thing and we replace this intersection by mid. And here is the point that number 2 and number 3, these two notions will coincide if we are in frame. Obviously, because we do not have multiplication, you drop this multiplication by the mid, and then strongly reducible ideal or elements, sorry, will coincide with the corresponding notion of prime element. So this is one of the very specific case where we can see the difference or the purpose of the extra multiplication operation in the multiplicative lattices. Similarly, we can define the radical of an ideal or radical of an element. Just replace the ideals by the elements, and then intersection by mates. And generally, we replace these finitely generated ideals by the corresponding notion of compact elements. That compact definition is very much similar, like how we define the compact set in a sense of topological space. So this is a standard way how you actually do the transitions from different kind of ideals. I mean, this is a sample that how to transfer the definitions from ideals to the corresponding type of elements in a multiplicative lattices. I mentioned multiplicative lattices. Of course, this can be further generalized to one of those, the last one, or the quantales. Then you can drop the commutativity, you can drop associativity. In fact, the spectrum of prime elements, which this Gianalisa, Finocchiaro, and Facchini paper actually considered in the last most general type of setup. And similarly, the other ones can be done. Of course, when you generalize your structure, you will lose some properties which is absolutely natural. And when you take multiplicative lattices, you may get something more. Now, once we have seen how to work with a class of ideals, now how to work with a class of element. Okay, very natural. Now we are in a better situation because we already know how the ideals behave in a ring. So now we wanted to see how much these things can be extended or can be studied in a lattice point of view. So let's take an example. Okay, let's take something called D ideals. Okay, so let us recall what is an annihilator. Annihilator is the of an element is the elements of the ring which kills that element. So what is a D ideal? D ideal is that if you have two elements, if annihilator of an element is contained in the other, if one of the element is there, then the other element is there. Then you can actually, without any effort, immediately can convert it to the corresponding element. You exactly define annihilator as it is because we have multiplication in our multiplicative lattice, and then the annihilator element will be exact copy of that thing where you replace this the containment with this less than equal to, which is very obvious. And it is also called a bare element because it was studied for bare rings and then has been generalized to multiplicative lattices, and they termed it as a bare element. So we also actually did some study on this D elements or bare elements very recently. So some of the standard questions, what you ask with a class of elements, the first thing is that we ask, are these elements closed under intersection, sums, and products? So if you have two D elements, are the sum of two D elements is a D element. If you have two D elements, is the product is a D element. I mean, this is a very standard closure property we generally ask. Sometimes the answer is yes, then it's good, we have a proof. Sometimes the answer is not straightforward, that means it's not true for any multiplicative lattices. Then you have to ask for which type of multiplicative lattices we can get such kind of closure property. And you will be lucky if you can characterize such multiplicative lattices where that kind of closeness is happening. And here is one example that we found that if we wanted to check when the product of two D elements is a D element, and then this strange kind of inequalities would hold. If you are not familiar with annihilator, it looks very strange to you. How can you kill a person twice? You cannot kill a person twice, right? I mean, you kill and kill. But believe me, you can kill only twice. If you kill third time, it will come back. So annihilator will be annihilator. So we can afford to kill maximum two. So it's not a typo, it's a very standard result. And it turns out to our surprise when we have this paper that this result even not been proved for the rings. So even when you study some kind of elements, there are results which has not been investigated to the corresponding ideals for things. So it can be done from here. Here is another question that, okay, this I already mentioned that if the positive, then what shall we do? The next question is that if you have one specific type of elements, how it is related with the another type of elements which is very close to it. For example, the bare elements are very close to Z elements, and this result is very much known in ring, that if your ring is semi-simple, then your bare element actually becomes Z elements. Then it turns out that you can actually prove the same result for elements. Of course, the proofs is different because of this lattice structure involvement. Uh, then the natural question is, another natural question is how they behave under multiplicative lattice homomorphism, because this is also very standard question that if you have a ring homomorphism, is the inverse image of an specific type of ideals becomes that specific type of ideals, which is not in general true. For example, if you take prime ideals, inverse image of a prime ideal is a prime ideal, but if you take a maximal ideal, it does not behave well. Inverse image of an ideal is an ideal, but the direct image, of course, behaves always very bad way compared to the inverse image. So you can ask the similar type of questions with this element version with any classes of ideals. What are the other properties of the corresponding ideals you can actually extend for the multiplicative lattices? So here are some guiding questions, very natural and obvious guiding questions, which can one explore when we wanted to work with a specific type of ideals. The next one is we wanted to introduce a closure operator, very similar what we had for K ideals, but this closure operator is very generic. Generic in the sense that if you take any element, then take the all elements of special elements, which is above it, and then take the meat of it. And if you see this definition has nothing to do with the bare element or D element. I mean, you can just blindly copy this definition with any class of ideals, with any class of elements. But still it will give you the smallest type, that type of elements containing that. So there is nothing very special with this, but it is very effective, again, to study special type of elements within that element, similar to the K-ideal closure operator, which looks different than this one. So here are some typical properties which you can study with this kind of closure operator for any different classes of elements. Notably, this number 8 is not in general true. Number 9 also in general not true, that it preserves the product. And that also plays some roles in some of the proofs. So, for example, B multiplicative lattice is a special type of multiplicative lattices where we actually have this kind of equality. The problem is even the product of two special type of elements may not be special type of elements. So that makes your complication harder here. Okay, so we captured all these this type of results for the bare elements. And then we did the similar kind of study for the Z elements, very similar ways how we talked about this one. Now, after algebra, let's see some topology. Okay, so what is our goal? We wanted to study any class of ideals algebraically, and similarly any class of elements. So similarly, if we wanted to talk about topology, our topology should be good enough so that we can endow it or impose it on any class of ideals. And in general, we cannot have that luxury beyond these strongly reducible ideals by these Hull kernel things. But we always know from our general topology honors course that when you are completely helpless, start with any subset, generate a topology. And that's called subbase topology, because you take the subbase, then you get the base, and you then get the closed sets. So it's a very standard procedure, and you do not need any conditions on your class of subsets because you can always check finite union arbitrary intersections and you can generate your topology. So nothing special about that. So when you wanted to endow this topology on any class of ideals, so we actually take the same things, because HK is a Galois connection which is only an algebraic closure but does not satisfy this Kuratowski problem, Kuratowski property, and that is why it fails to be gives me a topology. And this is called subbase topology, and it is already very well studied object in general, and it's called lower topology or coarse lower topology. But the question is studying this topology for all kind of ideals is actually something which, to best of our knowledge, was done not done before. So here is a typical comparison. with our nice topology, Zariski topology, which we put on prime ideals, and ideal topology, which you can put on any class of ideals. Of course, we cannot expect all the nice properties holds for Zariski will also hold for here, but it's good enough for many cases like compact T0 will work, connectedness behaves differently, sobriety holds. Of course, the third point from the top fails because, and that's a crucial point where you have this closeness property, and that's why you don't get the closed sets. So this is a way how you can actually cover any classes of ideals with a compromise of some topological properties which you cannot afford to have in this ideal topology. So we actually studied this and few other properties, and then we actually generalize it for any classes of elements. This is actually a suggestion where Professor Janelise told me that you are working with different kinds of ideals and put their topology there. What about this lattices? So it turns out that you can actually work quite well with the same strategy and work on multiplicative lattices. So I just didn't use the word ideal topology there because ideal is not the thing what we are doing, but I just keep the word lower and I just call it lower spaces. Uh, is it too bad name, lower spaces, or unacceptable? The lower spaces, the terminology to call them lower spaces. Okay, I got the message. Okay. Okay, sure. Thank you. Uh, so this kind of topologies, Zariski topology is a very special property which is called spectral spaces. And spectral spaces is a very special type of topological space which is quasi-compact. Please forgive me for using this quasi word again and again. Because when I work with these people on commutative algebra, they prefer the Bourbaki style. So quasi-compact is exactly what do you mean by compactness in general sense, because they do not want it to consider the Hausdorffness. So when I work with Themba Dubé, then it becomes compactness. When we work with Finocchiaro, it becomes quasi-compactness because they love the word quasi-compactness. And in general, we don't do in general. Those who are not working on algebraic geometry or commutative algebra, everybody agreed that we use compactness, but in those areas still they prefer quasi-compactness. But essentially we mean the same. Then we have a basis of quasi-compact open subspace, and then quasi-compact open sets are closed. So this is a amazing result of Hochster actually characterized spectral spaces of prime ideals as this with a spectral space. So this is a very deep result, and the proof is also very involved. So the result says something like this, that if you give me a spectral space, just a spectral space as a topological space, he constructed a ring, then take the prime ideals of the ring, then put Zariski on this, the Zariski topology on that, and that spectral space will become homeomorphic with your given space. So that's the whole constructions of this Hochster. So once we have the examples of spectral space, once we have the definition of a spectral space, the next question is, what are the examples of spectral space? That means which classes of ideals, when you endow this Zariski type of topology, it becomes spectral. And interestingly, we do not have many examples. The first example is thanks to Hochster himself, because prime ideals, that's how he experimented on it. The second example, we see if you take all ideals, then it will also gives you that if you put the ideal topology, it will give you also a spectral space. It comes from the Presley's work. And then, interestingly enough, that if you consider proper ideals, that means you have all ideals, then you remove the ring. So only you remove one element from your set. Then the proofs are completely different, because the argument works for all ideals, does not work if you just remove one element. And it turns out that you have an alternative way to prove that set of proper ideals actually a spectral space using this very simple, nice property, using the original spectral space of all ideals and then take a very special type of subspace of it. To best of my knowledge, these are the only three kinds of ideals on this ideal topology or Zariski topology which satisfy the spectral spaces. So it is very interesting to find examples for it. So when you do not find examples, what you do, you find counter examples. So what are the examples of non-spectral spaces? Okay, here are four different types of classes of ideals where we managed to actually prove that they are not spectral by constructing the counter examples. And that's where Finocchiaro and Spirito's expertise helped. And some of the examples are extremely complicated and convoluted constructions to prove that one of those axioms actually not satisfying to prove that they are not spectral. So the natural question is that can we characterize ideal spaces that are spectral, which is of course maybe impossible, if not very difficult to do that. The next question is how to do Hochstar type of constructions for even proper ideals, because we now know the proper ideals actually a spectral space, to how to construct that thing, which is beyond my comprehension and ability at this moment. So the question is, we talked about these ideal spaces endowing on any classes of ideals. Can you do the same thing for other mathematical structure? And yes, it can actually do similar kind of structures, topological studies on hyperrings, on monoids, on groups, on quantales, on semirings, on skew braces. If you take on submodules, different types of submodules, they have definition. And if you take a semiring and then you take sub-semi modules, you can actually endow the same kind of topology and study these kind of things. So you have quite open choices there. Now we can apply it for even normal subgroups. What to do that you take the normal subgroups, but you need a multiplication. So what we do, we just take the commutator and some specific things that you may not have maximal normal subgroups in general. So you need some kind of assumptions on your structure to do any kind of topological study before you start with. Then you can actually do the similar kind of things for semirings. One of the you can consider different classes of ideals and endow the ideal topology and study the semirings. As we know that semirings has one special type of ideals, subtractive ideal, which I mentioned, which disappeared in rings, because in ring every ideal is a subtractive ideal. And then you can do the same for monoid and consider both topological properties and spectrality. And you can even talk about semigroups and introduce different classes of ideals there if it is not there, and do the topological properties there. So is the subtractive spaces are spectral? At this moment, I'm not sure. The question is, if it is not, then the question is, if you have prime subtractive elements, ideals, will they be spectral? So that could be another interesting question. Then we can actually talk about hyperrings. So hyperrings is very much like ring, only you replace your binary operations with something called multi-valued or generalized functions or something like that, or hyper operation they call. So instead of taking product of two element as one element as a function, you take a set and subset of elements, and then you study very much similar like ring. And then we actually did some work with Karin and Bijan for this topological one. Then we have some very strange algebraic structure, and one of the most recently developed algebraic structure. This only came in 2017, skew braces. And the motivation again actually came from physics in quantum mechanics. It was braces, which was commutative version, and then they make it a non-commutative. That's why they called it skew braces. And it's actually two group structures which share the identity, and the distributive property between these two operations is a little bit strange, because the middle term, what we have minus a, which we do not have for case of rings. So by the way, one must be careful that skew braces is not a die group, because there is also a notion of a die group where you have two group structures, but die group is not just a set with two group structures, but with some list of axioms which must be satisfied. So die group is very similar to like this, but it has a different set of axioms. I forgot those list of axioms actually. So the question is how to define an ideal in a skew brace, and that's also quite involved. I mean, in general, we do not use this kind of functions and this to define ideals. So if when you have a definition of ideal in a skew brace, naturally we ask, what about the prime ideal in a skew braces? And this star is not actually the multiplication or the circle operation. It's actually one of the extra operation need to be defined. And this definition of a prime ideal is different than originally these people who came up with the skew braces have their prime ideals in their paper. And their prime ideals are is not similar or coinciding like a ring. So when I contacted one of the authors, is Benjamin, and then he said, you see, this structure is still very new and it should come up with new ideas. And then I contacted Themba, and then Themba and I actually come up with a new operations with that. And this does star. How does it look like? And then you can, using the definition of the star, you can define a prime ideal. Now, if you see, this definition is very similar, like a ring, that product of two ideals is below, then one of them is below. And then again, you can, since it's a nice, good prime ideal, you can put Zariski topology because it's very nice. And then you can study some topological properties on these prime ideals. Okay, so with that, so finally, based on all this whole thing, some broader picture of possible directions, what we can do from this general setup. One actually can think multiplicative ideal theory for multiplicative lattices. So ideals has two structure, one multiplicative structure, one abelian group structure. So there is already from 1960s research area called multiplicative ideal theory. So people wanted to understand how much multiplicative structure actually plays to study these ideal structures. And there are even books written on this multiplicative ideal theory. The question is, can we do the similar kind of things with the multiplication structure in our multiplicative lattice, taking this special type of element? So that could be one interesting topic. And then we already know that with ideals, we have this commutative algebra, then modules. So the question is, can we do the similar kind of things for multiplicative lattices? Because there is already a notion of modules over a quantal. Then the question is introducing study some classes of ideals and other algebraic structures which has not been there, and try to see their significances, not necessarily restricted to rings, but even to non-associative structures, even for skew braces, or even we can go very primitive ones like monoids and semi-rings. And with that, let me stop here. Thank you.
Thank you very much, Amartya. Any questions from the audience? Yes, of course.
I was intrigued by one of your slides in which you have an arrow pointing from quantals to quantum mechanics. Can you put that one up back? Can you?
Yes, I can put that back, but probably I will not be able to answer.
It's not necessary to put it back.
Okay, let me go back there.
But it would be helpful for the audience.
Yes, yes.
And they see the context of the slide.
No, it should be before.
I think you're almost there, yeah.
There is no way to start from the beginning, right? Yes, now I am almost there.
Yeah, that's it. Yeah, that's one. Yeah, can you lower it a little bit? Excellent.
Yeah.
So, so quantals is like a mathematical structure that, in some sense, serves as a mathematical model for various things. And one of those things is the algebraic structure of quantum mechanics, or one could say the logic of quantum mechanics. So my question is, the arrow that you have drawn there, can it also be reversed? Or in other words, do quantals possibly imply different kinds of quantum mechanical logic than the one that we usually physically accept as the correct quantum mechanical logic? So is the quantum mechanical logic unique if you start from quantals, or is it just one application of what you could call the quantal model? I'll give you an example in physics. So we have something called the Ising model, okay? Now the Ising model is simple and abstract and can model physical systems of various kinds. It can model critical phenomena in fluids, but it can also model critical phenomena in magnets, in certain magnets. And it can model all sorts of things. So this arrow that you have drawn from quantals to quantum mechanics, do we have to understand it that other quantum mechanics formulations or logics would be possible consistent with quantals, but not the same as the quantum mechanics that we have? Because the quantum mechanics that we have is not only like about non-commutativity of observation, but is also about the nature of measurement, right? So the fact that you can measure only eigenvalues of observables, I don't think is implied by the quantal model, but is an extra feature that reduces the possibilities of a quantum mechanics. Okay, so is my question clear to you about the possible existence of other logics and algebraic structures that could be physically interesting and that would follow from quantals, but may not survive the test with experiment?
Yes, your question is 100% clear to me, but I'm afraid I even do not know what is quantum logic. And the thing is that I just found in the work of this Mulvey, or as in the references, they said that one of the purpose of introducing this to understand this quantum mechanics, but I'm sure what you are saying, that it may model in one aspect of it, and then the arrow, what you are saying, the other directions may or may not be, but honestly speaking, I have no idea that how it can be done there.
Maybe just on the side of the question, what is for you the difference between quantum mechanical algebraic structure and quantum logic?
I never studied neither quantum logic or quantum algebras or these kind of things. Only the purpose of putting these connections or showing this arrow is just to tell that whenever you have an abstract mathematical structure, that does not necessarily mean it should be restricted within mathematics, because it may be connected to the other areas. And the very last algebraic structure, which I mentioned about the skew braces, is another very simple and very recent example where the braces came out of quantum mechanics, something called Young-Buckster's equations. I'm sure it's very familiar to you. So this kind of arrows actually to motivate, in some sense, to have some discussions between physicists and mathematics. But please forgive me for my ignorance about the physics or actual applications, or not being able to answer your original questions.
Thank you.
Well, at least we have some first questions to start the discussion, right? Any more questions or comments?
Thank you. Okay, first, let me comment on this question. I think this story is much more superficial, and the way quantum logic occurs is very, very simple, primitive. It is just that you replace conjunction of usual logic by product. Just like in algebra, you replace intersection by product. And that's it. It doesn't go deeper than that. So it's the answer is unfortunate. No, it doesn't help to anything. Why? You want to help? Okay, thank you. Now, may I ask my own questions? Amartya, first of all, you should take back your apologies because I think the talk was brilliant. Now, I have technical questions. When you say that your closure operator is not topological but algebraic, is it really algebraic? Because algebraic does not just mean that the closure of union is not union of closures. It also means that the closure of directed union is the union of closures.
By algebraic, I wanted to mean this idempotent property, and then A is continued there.
That's not called algebraic. That's called just closure operator.
Okay.
And then there are two special cases: algebraic, where directed unions are preserved, and topological, where finite unions are preserved. Okay. Second, why did you put cruel in there was a table?
Yes.
When you even kindly mentioned my paper with Italians, and you put cruel there. Why cruel?
But of course, I didn't read in details because it was not in English, that paper. But isn't it he was trying to do similar kind of inequalities in his structure to understand those ideals?
No. Cruel was predecessor of Dilworth and so on. What we did different, and what was the last line in your table, was the case where you do not require associativity.
Yes.
But you always do.
Yes, I do. Yeah.
Now, if you always do, then you lose your example with groups, because commutator is not associative. And in fact, we wanted non-associativity exactly because of commutators, not just groups, but many others. Okay, I will recall my next questions, and maybe other people will ask something. Thank you.
Thank you. Any more questions? By the way, I also want to make a comment. There is a second approach to quantum logic that was started by von Neumann and Birkhoff. And I think that is the one where it's more straightforward how to interpret the operations. With quantales, I think the interpretation is a bit more non-trivial as in Birkhoff von Neumann approach, but that's something we can look into in the future. Any other questions from the audience? If not, then maybe some questions from online participants. Yes, James? Yeah, sure, yeah.
So between, you had this case where you have no conditions, no associativity, but there's in the groups satisfy some extra identity, which is like Jacobi identity. 3 subgroups lemma, if you want to look it up or something like this, which holds in other algebras too. So it's not unique to groups, which I thought you might look at because maybe it gives you some extra bit of theory between the two. I don't know if maybe it's already done. I don't know. You don't think it will help?
Lie algebra. Yeah.
Yes.
Jacobi means is the same as Lie algebra that.
Well, you have to adapt it to a lattice, but
yeah,
but essentially yes.
Yeah.
Last question from the online participant. It's from Partha Ghosh, actually. And the question is, rings can be seen as monoids in a symmetric monoidal category. Ideals are subobjects of monoids with monoid action, and their collection is again a quantale. How much can your results be extended or known to exist in symmetric monoidal case?
The answer is I don't know because I never looked at monoidal categories or the results which can be extended there. But considering the fact that even yesterday, last evening, Zurab and I were working on some, I actually tell Zurab that here is something called a subtractive ideals, whether can it be extended to in a categorical level. And it turns out that you can do some kind of extensions in the categorical level. So based on that optimism, I'm sure many of these results may be or can be worked on monoidal categories. But honestly speaking, I never studied categorically these things.
Well, thank you very much once again. Still a couple of things to be done before we end the colloquium. The first thing is to present a Visarku volume to the speaker. Visarku is a magazine that publishes topics around psychology of abstract mathematics and science in general. And I think we'll also have a photo with that presentation. The second thing to do is for me to tell you that the next talk, the coming Monday, will be a panel discussion and a Q&A session on African artificial intelligence. It's a book that is published by Dr. Mart Nasila from First National Bank, and he will be joined as panelists by Professor Bruce Bassett from University of Cape Town, Professor Kanshukan Rajaratnam from Stellenbosch University. This is Kanshu. And also Professor Francesco Petruccione, NITheCS director. And that's happening next colloquium coming Monday.